I did this project back in grad school, and I wrote it using Reaper, and their Latin name is pretty funny. It's called albipinicens. The actual rock ants. Yeah, I did using Reaper, and my Haskell wasn't that good back then, so it was running like for hours and hours, using up all my memory, crashing most of the times. But I did produce a project and got a really good grade for it. Now I thought we need to revive that using Massiv. Have anybody here done anything like agent-based modeling, anything like that? Yeah, you guys familiar with the concept agent-based model? Yeah, it's a similar like cellular automata, where you have cells that have state, but it's a bit more complex. I probably should wait. I don't think anybody else is coming anyways. Where each agent, it's a conceptual thing, agent, whatever that might be, knows how to do certain tasks, knows how to do certain things, and might be able to communicate with others. So things like ants, there's bees, I don't know, little things, just simple conceptual things like a professor that was teaching at my university, University of Mexico. They did a few agents just sitting in the middle of the array, and all they do is just, okay, if okay, now officially started. If this neighboring elements, one is bigger and another one is smaller, then go ahead and swap them. If not, just continue. And on one side of the array, there is going to be producing agents that produce numbers, and the other, and there's a couple of those middle sorters. So you get a distributed sorting algorithm like that, where just an agents, they don't know anything about the whole picture, but just about neighbors, and they can sort the moving things. It's pretty cool stuff. Today we're gonna, by the way, if you want to clone the repo and build it, you're more than welcome to, but there's not going to be any separated examples. It's one big chunk of code. I'll try to go through it and try to explain how it works. Mostly the array stuff, the actual heuristics and logic of how ants move, I'm not going to try to bore you with it, because it's a bit mundane. Let me go ahead and first show you and explain what I mean by agent-based thing.
There's something wrong with the right side is cut.
What's wrong?
The left side of the
Oh, I see. We can fix it in a hacky sort of way. I'm gonna do it. Ah, come on. How about now? Is it better? A little more. Yeah, that looks good. Let's run this thing. It's one of the stages of what I'm going to be talking about. This is the world of ants. Okay, they used to live in this nest. Their nest is destroyed, or they just really need a new nest because there's too many of them there, and they need to find a new one. These little dots, every single one of them is an ant. There is a brood that it doesn't move around. There is a queen somewhere. She's red. I think that's at the top. She also doesn't move. Blue ones, they are worker ants. They're doing something, whatever task they do inside of the nest. They don't participate in the process of figuring out the nest. And the ones that are running over here, they are scouts. There's about 30% of all ants. They are scouts. They're trying to find a new home. By the way, fun fact: all ants are females, so they're all sisters. Another fun fact is they pretty much blind, so they can see with their antennas in front of them, but they don't know anything about the big picture. They can leave pheromones, but when they run around, they do not leave any pheromones. This particular species, at least. And they run in a random fashion. It's sort of like Levi flies, so it will be going on a straight line for a while, and then do a random decision in which direction it's going to go. You will see how they actually move once we get to that. So here's the few simple rules that they follow. The scouts. I'm talking only about the scouts. They're going to run around for a while. If they don't find any of the nest, each one of them, they'll go back into the home nest, hang out over here for a little bit, and then they repeat the process. Once one of the scouts finds the nests, either this one or this one, they will run around and try to think for themselves, how good is this nest? In real life, what they do is really, really cool. They run around, they leave the pheromone in random fashion, then they leave the nest, they run back in, they run around, and this time they don't leave the pheromone, but they count their own pheromone when they encounter it. And this way, they can precisely calculate the area of the new nest. It's really wild, so ants can count. I didn't implement that feature, I just artificially set the score on the nest. This one's like 0.9, this one's 0.7, so this one is worse, this one's better. Once the ant decides what kind of quality of this nest is, leaves, walks around for a little bit, depending on how good the nest is, it takes a longer or shorter time to decide, okay, I'm gonna try to recruit others to this nest. They turn into recruiting mode. Right? Run in a random fashion, go home on old home and try to find one of the scouts and try to tell them, follow me. Okay. Then it's called tandem leading. There's going to be two ants kind of following each other to the new nest, and the sister ant that was followed, she's going to repeat the process, decide on her own. The point is, with this simple rule, once the quorum is reached, there is some sort of amount of 10% of all the ants is inside of this new nest. The scout's just going to start carrying everybody back, like picking it up, carry, pick up, carry. With these few simple rules, they are always able to decide on a better nest, whatever in the neighborhood. So it's a collective distributed decision process making. This particular example or project, if you wish, is really array heavy. That's why I chose it for presenting for Massiv. There is quite a few things that we need to worry about. First of all, there is an image. Right? We need to produce an image. That's an array of pixels. Then there is a grid, each cell in a grid in the map. That's an array. Then we have an array of ants. Okay. Then we have an array of nests. We need to think about that as well. It is possible to implement this project just in pure fashion, like constantly creating new arrays and such. But it will be inefficient, I would think. So there is going to be a lot of mutation going on here. We're going to be writing like Java-like code in Haskell, but it's still type safe. It works. And there is one twist to this thing. Each ant runs in a separate thread. Okay, so it is possible for two ants to be next to each other and try to make conflicting decisions. Let's say try to move in the same cell at the same time. And we will see how a nifty trick that we can use in order to avoid this kind of race conditions. There is not going to be any concurrency again. There is not going to be any M bars, any locking, which is great because it's easy to introduce deadlocks and things like that. So yeah, does this whole thing make sense? Any questions about that? No?
Using green threads or ROS threads out of curiosity?
It's green threads, yeah. Remember when we were doing par, it would just create as many threads as there are capabilities. Here we're going to do par n and give it how many n's we have. This way each n will be running in separate thread. Most likely. Sometimes it can be possible that one thread will make a decision for 2 n's or something like that. Oh, and just to show you how they move, it's something like that. Okay. Yeah, I think that's all I had to say about it. Let's go. First, at any project, I always look at types. Let's look at what we have here. Cell. It's just a new type around an int. And what we're going to do is -2 is a wall, -1 it's an empty cell, and if there is a positive, non-negative number, it's an index of a nest. So you're going to have an array with indices which is where the nests are. There is the information about the nest. We have a quality of the nest, size of the nest, and where it starts on the whole grid. And we need to describe where the entrance to that nest is. Oh, one more important thing. I don't know if you noticed on the image, we're going to be looking at hexagonal grids. So it's not going to be, the n can move not in 8 directions, not in 4 directions, but in 6 directions. It will have a 6 neighboring cells. And I'll try to explain how that works with and how do we map it into the array itself. Now, here's the tasks I was telling you about. And then either searching, hanging out at home, figuring out what kind of nest it is, recruiting, leading, another enter, where the other one is following, or transporting, just carrying it. What are those things here? It's not particularly important for what I'm going to be talking about. This is the important part. The state of end, it can be idle or busy. If it's idle, then it can make some sort of decision for himself, or somebody else can make a decision, change his task. If it's busy, that's it. Nobody can touch it. It's making a decision. This is sort of like a baton to make sure that there's no race conditions. 3 end types: worker, brood, queen. The end has an index, which is just its index in the array. Now, how many of you played around with IORFs? Okay. What is IORF? It's your regular variable in any other language, which just holds a pointer to some object, let's say in Java, right? If you pass around, you can mutate at any point. It's mutable variable, basically. That's what it is. And we have same thing, IORF, with a set of nests that it has discovered. Now, this is the important stuff. We have a grid, which is a mutable array, a 2-dimensional mutable array. This means it's mutable, and it holds indices of what is it? Of n's. So whenever an end moves, we need to update that index. We have array of all n's and array of just workers, because they only the ones who doing decisions, who moving around and stuff. Now, this is a tricky thing that does the drawing for us on the image. I'm going to talk about that later. Now we have array of nests, as I was telling you about, a 2-dimensional array of cells, so we know where the nests are, and we have a base image. So we draw it once, and then we're gonna mutate it whenever we want to place the ends on it. And this is just a number of steps, it doesn't matter. Now this is our environment. This is the whole thing that we have for simulation. We have a colony with ends, we have the grid, and this is the stuff for Rio. If you never used Rio, I would highly suggest to play around with it. It's a package that we developed at FP Complete. It has all batteries included, but I'm not going to talk about it here. It's just needed for logging and stuff. We also need a random number generator. This is a generator from a split mix package, which we'll use to create, decide where I'm going to turn and such. And some constants, which are helpful for making decisions. A few helper functions. I'm not going to go too deeply in it, but there is a few things I want to point out. This is the indexing function I was talking about. It's in a monothrow. Here what we do is we give it a sensible error message. From maybe, if there is no nest, then we can't do anything, throw an error. Now, here's the cool part. Think about ends as separate threads. And let's say we have a cell here. I'm just going to draw them as circles right now. Right? And this is an end, this is another end, and they, at the same time, they want to move into the same cell. Okay? What happens? Arrays condition. If we want to update inside of the array, we want to update this location, but only one of them can move there. How do we solve it? There is an atomic operation on arrays that holds integers, just a regular 64-bit int. We can write there atomically, we can read there atomically, that's usually the case. But can we modify it atomically? That's a question. For example, we want to place an ant in a cell. There is a thing called cas. It's known in other languages. It's called compare and swap. What you do is you give it a value that you expect to be in a cell or in a reference, if you wish, in other places like IRFs. You give it a value that you expect it to be, and you give it a value that you want to write into it. And what it's going to do, it's going to return you the old value, and if the value that you told it expected, it was exactly the same, it will update it. So what happens here? You both of these ends, both of these threads, you tell them, you write your index in this cell, but only if this cell is empty, if it has a negative value. And then once this operation completes, like here, you will get a previous index. And what do we do here? If previous index is an empty cell, that means we successfully wrote this index into this cell. If the previous was wall cell, that means the update didn't happen. Hit the wall. You can't go there. Otherwise, there was an occupant there with this index. So the update didn't happen. And this way, we can atomically resolve the situation. Does it make sense? Any questions about this cool concept, compare and swap?
Isn't it the same concept with transactional memory?
No, it's transactional memory is quite a bit more complex than that. I'm not even sure how it's implemented, to be honest with you. I don't know how to use it very well, but there is a separate TVAR, transactional variable, and you can roll a bunch of transactions and stuff. This is just an atomic operation. There is a similar concept for IRFs. That's what I'm going to be using or abusing as well. Now, here's the cool thing. I'm not going to use it here, but I'll explain how it is implemented in Massiv if we want to atomically modify a cell. If we want to atomically modify, we just keep this in a loop until we succeed. Okay. This throw string is just an exception thrower. That's why we have to leave it in monad.io. Okay, and similar thing for removing an ant. We give it an array, we give it an index which we operate on, we give it we expect there to be an end with this index there, and if we want to remove it, we want to write an empty cell in there, and it does similar things. Except here, if there was no end at specified locations, it means it's bad. There is a bug in the program.
Can I ask a question?
Sure, yeah.
I think I'm not understanding something with the coerce empty cell. So why is that the same value both for placing and removing? That's not your expected value, right? What is it?
This is the expected value here, and this is the expected value here.
Oh, they're swaps. I didn't notice. Got it.
Yeah.
Sorry, I didn't notice the arguments were swapped.
Yeah. By the way, have you seen chorus before? Yeah, it just unwraps the new type for you. Oh, here we're using new type just for the type safety, just to make sure you don't mess up the indices. And all of these extensions, almost all of them, are necessary to derive this prim type class. But you don't need to worry about them.
The second argument is what you're writing. The first argument is what you're expecting. Other way around?
This is what you expect.
First argument is expected. Got it.
Yeah.
Thanks.
Absolutely. Now we get into the grid scale. What's a grid? Grid. Have you ever thought about hexagonal grids before? Apparently, in the nature, it's the best way to spend the environment efficiently. That's why bees have their hives in hexagonal grids. Let's draw it. I'll just draw a few cells. Hexagonal grid, right? But if we shift these two up, this is just an array. It's an array 2 by 3. Believe me? Yeah? That's all it is. And you can make them bigger, right? So this is all just index manipulation. Let's draw a couple more. Therefore, an end can move in either of those 6 directions. It makes. Has anybody played Fallout, the game? How about the second part or the first part? Yeah, a long time ago. The guy was running around like a stupid idiot. Yeah, that's why.
You only get one cardinal direction, so it looks unnatural in one.
Yes, exactly. Yeah, so you can go up and down, easily. But if you go like that, yeah, you run like an idiot, like a drone. Yeah. The way I drew it, it's actually flipped in the implementation here, so maybe messed it up a little. Now, this looks nice as a geometrical object. What do? We need to draw them somehow. And in order to draw them as pixels, we need to actually not figure out the geometry, but actually write the pixels. If we want to scale 2 by 2, I'm horrible at drawing. We just basically drawing a bunch of crosses like that. Actually, I'm going to show it later as an image, so you'll see it. This is what exactly this is for, those grid scales. This is important because there is a lot of array trickery in there, and we'll see it. Right now, let's continue with types. Here's our specification of a grid. This is what kind of size it is. The scaling factor, if it's 3 by 4 or 5 by 6, scaling. And here's an array of our nests. In in the example I showed you, there's only 3 elements in it. This is just a configuration for the whole thing, not particularly important. It's just an initial start and stuff. How many ends we have and so on, and like initial seed. So we can, if we run it sequentially, we can actually reproduce results exactly on each run. Now here's how we create a new colony. This is fun. We take the grid map, which has indices of our nests. We clear the indices of the nests. We keep the actual grid map, and we call it the colony grid. And then we're going to mutate that mutable array and write the location of the ants in there. Here's we initialize how many of each there is, of workers, brood, and queen. It's all delete array, and then we can cut it. Here's how we create a reference. It's just new IRF, and you give it a value. In this case, it's a singleton set with no elements. Oh no, with the 1 element, 0. This is the nest that entered and then discovered. And let's look at this ugliness here. We have initialized ant types. We compute that array, and then we traverse it, initializing each ant. This gives us all ants. Now here's the cool part. The array with ants is also array with workers, but shifted a little bit. We just extract a portion of array, but we never create a new array for those workers, which is good for performance. Now we do even more. We extract 30% of it for scouts. Therefore, it's easier for us to figure out which ones are actually doing the productive work and stuff. Yeah, and then we initialize the scouts as they're going to be just hanging at home. It'll be updated for them to scout and stuff like that later. What do we do for initializing the actual ant? We get available spot. Let's take a look at that function. Give it an ant index, and we give it a region which is somewhere at home. Get available. Let's see. Is it too big? Too small? Bigger. Let's do this. Okay. Get available spot for this is just right here. What it's gonna do? It's gonna call random element. What do we need? We have an array of indices, and we want to choose one that we at random where we want to place an ant. And this is this random function. If array is empty, return nothing, which should never happen. We don't want to call that, but then what we do, figure out the linear index, linear size. We figure out how many total elements in this arrays, and we just generate a random integer from 0 to 1 minus the total elements. And then we evaluate this array. It can be delayed array, but we evaluate only 1 element, so we don't care if it's delayed or it's any other representation that can be a source array. So we don't worry about the duplicate evaluation at all, because we only care about 1 element. Alternatively, I could create an instance for random for 2 dimensions, but it's easier just to deal with int and call this from linear index. Now here's the important part. I could have just as well written something like this, and it would compile, because maybe is also monad throw, but then it would be buggy. If we really want to fail loud when the index, the generated index is wrong, because that means our random number generator produces bogus numbers, and we don't want that to happen. We want to catch that. And the other random stuff is not terribly important. This has stuff is also implementation detail. Don't need to worry about it. For all purposes, this module just generates random stuff for us. That's why it's called random. Yes. Oh, there's something I forgot to do. While I'm going to be continuing talking, I'm going to set it to run, because it takes about 10 to 15 minutes for the 20,000 step to create 20,000 images. And then we'll see if it actually does something cool for us or not. Okay?
I was trying to ask what it's supposed to look like. So it is just supposed to sit and run at the command line with no visuals until you're done running the whole simulation?
Let's see.
That's what I got.
Okay. Yeah, it uses a sticky login from Rio package. Okay, random, we're done with random. Okay, now we initialized our colony. So if you've never seen this before, it's record wildcards. I usually try and recommend not to use them, but I still use them sometimes. Before we go into the actual simulation, what we want to do is look at how it starts. This is how we initialize our grid. We actually use this particular one. So this is a home nest. We give it where it's located, where the entrance, and so on and so forth. Just like you saw in the image. This is just the indices of where everything's located. Then the extra 2000 for ends to really decide how long they can run for. It's not important. Now here's our configuration. We give it a seed for random number generator. We give it this whole thing. How many workers? Total 150. 20 brood. Steps, not important. Some constants, also not important. This is for how they're going to be running around. And maximum number of steps, which is the number here. Yeah, 20,000. And we run our simulation. This is Rio-specific stuff. Here, it's what we basically are doing. We're removing anything that was there before. We run our model, starting with 0, and at the end we make a video using FFmpeg. What's run model? Run model, it recursively calls itself fairly straightforward. We make a colony image. We write that image to the, this is actually from the Massiv IO package. We write that PNG into this file path. Then we do one colony step, which is a function with no arguments, but it does a lot of mutation behind the scene. And then we continue running our model until we reach the maximum number of steps. This is how we run FFmpeg. If you care how to do that, not important. What is important is, how do we make this image, make colony image? It also has no arguments, which is some sort of magical thing. Let's look at this. Okay. The reason why it has no argument is because it's a monad reader. Are you familiar with monad reader? Yeah. Basically, you can call an ask function and get this environment out of the monad, and then you can operate on it. All we care about is the drawer, the cell drawer. We care about the grid image, the initial image, which is a pure array with pixels. And what we do, go with MRE. What it's going to do, it's going to make a copy of this image, which all it has is just white pixels and what do you call them? And walls. And we're going to place the ants in there. for each end, we do it in parallel as well. For each end, we grab its location from this IRF. We get a color depending on what this end is doing, and then we draw them using some magical grid cell drawer. This is how we draw it. We give it a function that can write into this image. See, write image, this index, and we write the color. Okay. Does this make sense? Okay, good. And at the end, this produces for us an image of color space RGB with word 8. And this is all it is. It's just a type synonym. Image that is array. It's a two-dimensional array with pixels of some color space. Also, it comes from a Massiv IO package. Oh, and underneath it uses a cool package called Juicy Pixels, pretty famous one to read and write images. Yeah, this is just a conversion from a state to a color. Now let's look at this draw cell thing. Or is it? No, let's go from the top. How we make a grid? Getting dizzy from all the talking. Need to remember to breathe. Yeah, faster I'll go through this stuff. Maybe more cool examples we can hack on this next session. What do? Create a grid. We make an image and we make a grid map. Let's look at make grid map. We create a load array. If you remember, this is a way to do mutation without actually doing any mutation. This is a delayed representation. We give it a size of this array. The default element is empty cell, so it's going to be initialized with this default element for us. All we need to do is fill in the walls. And here's a cool trick. Instead of doing bounce checking at the border, what are we going to write? We're going to just fill it as a wall. This way, an end cannot pass the wall, and we never need to check is this index out of bounds or not. And it's a nice hack. Well, it's sort of like a real life what they did in model and real ends. They put them in a petri dish, which has walls, and the ends cannot escape. Now, for every nest, the I4, for every nest, we get an index of the nest, and we get the position of northwest side, position of this nest and its size. And we figure out the southeast part. We fill in the walls by using this function that gets a writer and actually fills in the walls for us. There's a lot of map M, a lot of monadic writing, but you see, it's all just arbitrary monad. There is no I/O or any nasty stuff going on. So we're doing pure mutation, which is kind of cool, I think. So yeah, we fill in the walls. We override the walls with an empty cell where the entrance is supposed to be. And we fill in the empty spots with the indices of a nest so we can always look up. Let's say an ant will always know if it's inside of the nest and which nest it is. Now here's the fun stuff. How do you draw an image, a hexagonal, with hexagonal cells? Same thing. We figure out an image size, which is just multiplication by the multiplier, how we zoom it up. White pixel is just a, black pixel is just a 0, white pixel is 255. Again, we fill in the walls the same way. It's very similar to this map here, except it uses the this cell drawer. Where is it? This here, draw cell drawer. What is this thing? Let's look at this. Okay. Get cell drawer. Depending on which type we set, it will give us a specific function that cares about the size of the cell and the offset and stuff. And then the actual function that will be drawn. Now let's look at this. A 2x2 zoom up is this function right here. What does it do? How would I show it? Draw cell. Okay, let's look at more complex examples. This will make sense. So this is our 7x6 blow-up thing. This is how we draw a hexagonal cell. Let's look at the example here, so it will make more sense. Okay. See if it works? Okay. This is how it looks zoomed up and then even blowed up. So each one of those is a separate pixel. Okay. So this is our hexagon, and yeah, ends will be moving sort of in this fashion as well. Okay, makes sense. Yeah. Yeah. And
what do you select between the different sizes of the grids that you're drawing at? Do you have a mode that kind of zooms in and out depending on how large you want your visualization to be?
no, it's whenever it writes, it just writes. You set this data type in the beginning.
It's a global. It's like one global setting for your whole.
Whenever you do a configuration, yeah, let me show you. Whenever you do set up a configuration, you specify it. Let's look at run. Oh. Yeah, whenever you do grid spec, you specify which size do you want it. And in the particular run that is going on right now, which is at 17, it's almost done. It's 3x4, but right now we're looking at 5x6. Okay. I don't know if you, well, actually, you know what? Let's not change it. I don't know if you noticed, but this thing also was zoomed up more, and there was sort of a grid drawn, so we can separate the pixels from each other. I want to talk about that function, because this describes, they're kind of self-contained, and it describes well the difference between delayed and delayed load array. Actually, added this function to the Massiv, so it's available there for arbitrary dimension, but let's talk about them here. The result, once you compute these both arrays, these both functions will produce exactly the same array. What's the difference? One uses make array, another one uses make load array. Okay. With make array, we have to iterate each. First of all, what it does, it blows up the size by the zooming factor, which is a k plus 1, because we need to add one more pixel at the border. It blows up by k. The actual size is m by n. That's the original size of the array. Then we multiply by k, adding plus 1 to each, and we use this get new element function to produce each pixel. And for each of them, we check. If it's divisible by k, use 0. If it's or it's divisible, j divisible by k, give it a 0. Oh, if it's divisible, then we do a grid value, which is just a great value for the grid. Otherwise, look up the original value, and so it sort of replicates the same value within that. that is a little bit inefficient. What we can do is initialize an array with the default value, which is grid value. So we create, it will create for us an array with just gray pixels. With a similar way we figure out the size, so this part doesn't change. But then we iterate over the original array. And for each index and element, we're gonna create sort of a loop. This map M will just create a loop for us, where we just replicate that element many times for this particular pixel. First of all, it's cache friendly. We never had to do any modular division. There is no if statements. And this turns out to be like 100 times faster than running this. Go figure. By the way, have you ever seen inline pragma like this? Very often it's important to add this. What it's going to do, it's going to, whenever it's generating core, it's going to grab this whole function and inline it at the call side. Massiv is, it has every function, almost every function, it has this inline pragma. If you don't, quite often it's not going to be able to optimize it as well. And especially if it's a function that is being called a lot, it will have to call each time, and it also generates a much slower code. So it's quite important to include it, and especially for delayed load arrays. So sometimes the GC can figure out if it wants to inline or not the delayed array, but delayed load array highly relies on. My general suggestion is all the functions you write with Massiv, just put inline pragma on it and forget about it, and it just increases the compile time. Sometimes you need to think about whether or not you need it, but it's not going to be a talk. I'm not going to be talking about it. Okay. We did figure out how to draw this image. Does this make sense, the actual image generation part? How we map from an array to an actual image? Okay. Now, please shoot the questions at me. Yeah, this is kind of fun. You can actually continue exploding. You could reuse the smaller functions for this, but this sort of depicts how are the elements actually written, which is nice. Yeah, I think this is all I had to say about the grid. Then whenever ant moves, the ant doesn't know indices, it knows directions. It knows the direction from 0 to 2 pi. So we need to convert the 0 to 2 pi into the actual indices. And this is what happens here. For example, if we have an index of an ant and we know his direction, we want to produce an index. And here is some trigonometry sort of thing that, that does this for us. I could never know if it's true or not, if it works correctly. And this is the opposite thing. If we have an index and a neighboring index, we want to figure out the direction. So what I did is I created a gradient, just to test my sanity if I'm not doing anything stupid. So let's go ahead and look at how it actually looks like. The image. Gradient. See if it's gonna work. It's working. I think it's thinking. What it does is just creates an image, and for every pixel, it will draw it in a separate color as a gradient. Okay, our simulation has finished. Good. I think it will show at some point. It runs in GHCI, so in GHCI the Massiv code is usually pretty slow. If you want to do something computation heavy, you want to compile it with optimizations and thread it, so you can do everything in parallel and do it fast. At some point it'll finish, I promise. Let's see if it's actually running. No, it's not. Wonder what happened. Let's load this thing. Oh, I know what happened. This display image function is a non-blocking function. Okay, there you go. So, it's like a gradient. Depending on the angle, it gives you a different color, right? And it's also a hexagonal grid thing. And similar, there is a bunch of helper functions in the array that deal with mutation. So in this particular thing, what happens, it grabs just an empty image, and it gets a mutable image, and for every cell, which this thing describes, it creates a for loop that iterates over the array, and then uses the grid cell drawer that I showed you before. It writes this color into the cell. So that's all it is. Okay. You ready for some scary stuff? This code is going to be not very array heavy. This is just decisions and how ends move. I'm not going to talk too much about it. There is things like look up the current location from the grid map. We're using the index operator. But otherwise, if you're really interested, you can try to go through this and email me some questions or open issues if you wish. It's open source. By the way, here's the repository for it. It's hints rock ends. Okay. But the gist of it is the ant can walk inside. Yep. 5 minutes, cool. Oh, actually, no, it's a break, right?
It's 10. Yeah, it's break 10.
9.5. So that means it's a break? Yeah? Yeah, okay. We're going to finish it up real quickly in the next session, and we'll see the demo.